Okay, so our next example, we're finding another inverse Laplace transform. And in this case, the function that we're working with doesn't really look exactly like any of the functions in our table. Our denominator is a little bit more complicated looking, and the trick here is to use partial fractions to break this thing up into smaller chunks, which will more easily match the functions that we're seeing in this table. And partial fractions is something you're going to be doing a lot of in this chapter. So if it's been a while, you're going to want to brush up. So what I want to do here is take the expression that I'm trying to take my inverse Laplace transform of s over s plus 2 s squared plus 4, and write it using its partial fraction decomposition. So a over s plus 2 plus bs plus c over s squared plus 4. If you don't remember with partial fractions, when you have a quadratic factor that's irreducible, meaning I can't factor this any further, then the numerator has to be a linear polynomial. It's not just a constant up here. So this implies, if I multiply both sides by this denominator here, that I have s equals a times s squared plus 4 plus bs plus c times s plus 2. Okay, and again, we've done some partial fractions in this class before, but my preferred method for dealing with partial fraction decompositions is to plug something in for s that eliminates some of your unknowns and helps you solve for the other unknowns. So for example, looking at what I have here, if I plug a negative 2 in for s, this goes to 0, taking this entire term to 0. That leaves me with this. When s equals negative 2, I'm going to have negative 2 on this side. Negative 2 equals, if I plug a negative 2 in here, this becomes 4 plus 4, or 8 times a, which implies that a equals negative 1/4. Okay? Now, if I wanted to do something similar to eliminate this a here, then I would need to plug something in that would cause this to become 0, but no real number can do that, because anything I plug in for s, if it's a real number, will make a non-negative number here. Plus 4 is going to be positive, not 0. But you can do this with complex numbers as well. For example, if I plugged in a 2i, if s is equal to 2i squared is negative 4, plus 4 is 0. So that causes this term to disappear. This s becomes 2i, and on this side, I'm going to get b times 2i plus c times 2i plus 2. Okay, and what you would want to do here is multiply this out and write it as you would a complex number with a real part and an imaginary part. Doing that in this case will give me 2c minus 4b plus 4b plus 2ci. Okay? Now I have a real part and I have an imaginary part, and that's supposed to be equal to this complex number, 2i. The real part of this complex number is 0, so I can set that real part equal to 0, giving me 2c minus 4b equals 0. Or, if I wanted to solve for c, c is equal to 2b. Okay? Now, this second part, this imaginary part, should equal 2, because that's the imaginary part on my complex number there. So that means I should have 4b plus 2c equals 2. I can make a substitution now, c equals 2b, so that can get plugged in here, giving me 4b plus 4b, or 8b equals 2, implying that b equals 1/4. If I plug 1/4 in for the b here, to get c, I'm going to get c equals 2 times 1/4, or 1/2. So c equals 1/2. Okay? All right, so what does that mean? Well, the point of this was to break this thing up using a inverse Laplace transform, or sorry, to break this thing up using partial fractions so that I can evaluate the inverse Laplace transform. So plugging these things back up into my expression up here, I'm going to get, I'm looking at finding the inverse Laplace transform of the following. A over s plus 2, where a is now negative 1/4 over s plus 2, plus, I'm going to break this up into two rational expressions, so I'm going to have a total of 3 here. bs, b is 1/4, so this becomes plus 1/4 s over s squared plus 4, plus c, which is 1/2 over s squared plus 4. Okay? Now I could use my linearity property, and I'm going to show the steps here. In future examples, I might skip a couple of steps at this stage, but notice this, using my linearity property, can be written as negative 1/4 inverse Laplace transform of 1 over s plus 2. Okay, and now I'm going to be careful with this one. Oh, no, sorry, this one's fine. Plus 1/4 inverse Laplace transform of s over s squared plus 4. Okay, now this guy right here, this the form of this thing kind of matches what I have for my sine of kt, and I need to remember that the numerator k needs to come from the k squared showing up down here. So what that means, if my k squared is 4, I need there to be 4 right here. I need there to be a 2 left over. So instead of factoring just a 1/2 out, I'm going to factor a 1/4 out. So I'm going to make this plus 1/4 inverse Laplace transform. That leaves me a 2 up here. S squared plus 4. Now all three of these match the familiar forms that we recognize from our table. So what we should be getting as an answer here is, where did I write it? Here we go. Oh, hang on. I want to make sure I did that correctly. Yeah, okay. So negative 1/4. This is e to the negative 2t. That's what this becomes. Plus 1/4. This one matched our cosine of kt, so this becomes cosine of 2t. Remember, k is 2 here. Plus 1/4 sine of kt. That's 2t in this case. Okay? So that would be the inverse Laplace transform that we were looking for. All right, so now that we've had some practice with that, let's look at what it looks like to find the inverse Laplace transform of the derivative of a function, because this is where we can start using these in differential equations. Let's suppose I wanted to take the inverse Laplace transform of some derivative, f prime of t. Okay, this is just using the definition of the Laplace transform. Notice we're talking about the Laplace transform and not the inverse Laplace transform right now. Okay, so here's the definition of that. Now, as we've seen before, evaluating these guys usually requires integration by parts somehow. So in this case, I'm going to let u be e to the negative st, and my dv, when I'm doing integration by parts, will be f prime of t dt. That means that integration by parts will give me this, e to the negative st f of t, because that's what v would have been, from infinity to, or 0 to infinity, plus s times the integral from 0 to infinity of e to the negative st f of t dt. Now, again, we're going to be assuming that the function f of t has exponential order, and one actual implication of that will be that the expression in here, this expression right here, tends to 0 as t goes to infinity. The e to the negative st will sort of dominate the f of t and shrink this whole thing down to 0. So when I evaluate this upper limit of integration here, that'll go to 0, minus this thing evaluated at 0. Well, e to the negative s times 0 is 1 f of 0, so that becomes negative f of 0 when I evaluate this. This guy right here is just the definition of the Laplace transform of f of t. So multiplying that by s, I get this, or we usually write it in the reverse order. If the Laplace transform of f of t is denoted by capital F of s, remember it gives us a function of s, then we get this result. So what this has done is it's allowed us to take the Laplace transform of the derivative of a function and express it in terms of a function of s that involves just the Laplace transform of f of t instead of any derivatives in here. Okay, we can do this for higher order derivatives as well. Notice if I wanted to deal with a second order derivative, I would do integration by parts again. So here's my second order derivative being plugged into my Laplace transform, formula or definition. Using integration by parts will give me this. This guy right here, as we saw previously, is going to become negative f prime of 0 when you evaluate it at the limits of integration. And then this integral right here is the definition of the Laplace transform of f prime of t, which we just found. Right? Here it is, and here's what we found on the previous page. You distribute that s in, and now notice what we get. The Laplace transform of f double prime of t is equal to s squared, big F of s, remember that's the Laplace transform of just f of t, minus s times f of 0 minus f prime of 0. Okay? Notice f of 0 and f prime of 0, those are going to be constants. And generally, in the problems that we're working out, we're going to know those because they're going to be initial conditions that were given in the problem. So the f of 0 and f prime of 0 are constants. S is my unknown. And aside from this term here, all of this is starting to look like a polynomial, something in terms of s, right? And if we repeated this process, which we could do indefinitely, we could find a general formula for the Laplace transform of the nth derivative of some function f of t. So it ends up looking like this: s to the power of n, where that power matches the derivative of this function here, times big F of s, the Laplace transform of just f, minus s to the n minus 1 power f of 0, minus s to the n minus 2 power f prime of 0. And this pattern continues until we get down to this constant term, the n minus 1th derivative of 0. And notice the minus sign in front of that. Okay? So this is crucial because what we're going to be doing is if we were trying to solve a linear differential equation, for example, we could take the Laplace transform of both sides of this, use the linearity property to write it this way. Notice it's non-homogeneous, so I have this g of t here. And that means I'm taking the Laplace transform of that as well. Also, I have these initial conditions, which are going to be useful. Now, each Laplace transform showing up in this expression is the Laplace transform of a derivative. And we now have this formula for taking all of those and putting them in terms of the Laplace transform of just the function y, and then other functions of s kind of floating around in there. So when we're trying to find when we're using this method for finding the solution to a DE using the Laplace transform, I'm going to be using a capital Y of S to denote the Laplace transform of the function y that we're trying to find. But this kind of complicated looking expression here is the end result of taking a Laplace transform of both sides of that linear DE. And even though it looks more complicated, the crucial thing to recognize here is the only function that's actually showing up in all of this is that y of s. Everything else, even though you're seeing y's and y primes and y to the, the n minus 1th derivatives and all this kind of stuff, they're all evaluated at 0. Those are all initial conditions. So this allows us to get an algebraic equation, which you can then solve for y of s. Once you've done that, we can get from y of s to the function lowercase y, the thing we're trying to solve for, by then taking an inverse Laplace transform. Remember, the idea is to take us from that function of s back to a function of t. Okay? So, we're going to do a couple examples of this. I'll do one in this video, and I'll probably make a final video for the last one. It's a little bit longer. But for this one, I want to solve this DE, y prime minus y equals 2 cosine of 5t, and I have this initial condition, y of 0 equals 0. Okay? So the first thing I want to do is take the Laplace transform of both sides. And using linearity, this will be equal to the Laplace transform of y prime minus the Laplace transform of y, and that's going to equal 2 times the Laplace transform of cosine of 5t. Okay, linearity allows me to do that. Now, this Laplace transform right here of y prime, we just came up with a formula for that a few minutes ago. So what does this come out to? Well, it's going to look like s times, now in the formula that I showed here, let's actually go to the one that just has the first derivative. The formula that I showed here, I'm using a capital F of s, but remember, I'm going to start using a capital Y of s to denote the Laplace transform of my function y. So it actually looks like this. Okay, s y of s minus y of 0. This is the formula for this Laplace transform. Minus the Laplace transform of y. Remember, we're writing that this way, y of s equals 2 times. Now we know the formula for this, the Laplace transform of cosine of 5t, because this is from our table, right? That becomes 2 times s over s squared plus 25, okay? Now I'm going to do some cleanup here. So I'm trying to isolate the y of s. Notice that y of 0, little y of 0 from my initial condition is equal to 0. So this term will drop out. We're going to lose that. And then if I combine these two, I'm going to get s minus 1 times y of s equals, I'll multiply this and get 2s over s squared plus 25. Okay? This means that y of s is equal to 2s over, I'm going to divide both sides by that s minus 1 right there. S minus 1 times s squared plus 25. Okay? Now, remember, what we're going to want to do is take an inverse Laplace transform of both sides of this, because the inverse Laplace transform will give me lowercase y, the thing I'm trying to solve for. But, as we saw in the previous example, we can't do this directly. We need to make a partial fraction decomposition of this guy in order to find its inverse Laplace transform. So that's equal to a over s minus 1 plus bs plus c over s squared plus 25. That's an irreducible quadratic expression. Okay, so what does that mean? Multiplying both sides by that denominator, I'm going to get 2s equals a times s squared plus 25 plus bs plus c times s minus 1. Okay, and we're going to solve this in a similar manner as before. If I plug s equals 1 in, I'm going to get this entire thing going to 0, which is good. S equals 1 will give me 2 times 1 on the left side. Go like that, which is 2. Plugging a 1 in here, 1 squared plus 25 is 26, so this becomes 26a, implying that a equals 1/13. Okay? And as before, we saw that plugging an imaginary number in was helpful before. So if I plug in s equals 5i, that's going to cause this term to go to 0. Plugging 5i in here gives me 10i, and that's equal to b times 5i plus c times, I'm going to switch this around, call that negative 1 plus 5i. Okay? Multiply that out as you do with complex numbers, and what you're going to end up with is negative 25b minus c plus negative 5b plus 5ci. Okay? This guy, the real part, should match the real part of this complex number, which is 0. So I'm going to set negative 25b minus c equal to 0, and this implies that c equals negative 25b. Now this guy right here should match the imaginary part, so I can set this equal to 10. I'm going to have negative 5b plus 5c equals 10, but c is equal to negative 25b, so I can make a substitution here. That'll give me negative 125b plus negative 5b gives me negative 130b equals 10, or b equals negative 1/13. Using that to find c, I can plug this into here, and I get c equals 25/13. Okay? So that means y of s is equal to a over s minus 1, and a we found was 1/13. So I get 1/13. Remember, I'm plugging my a, b, and c up into this. 1/13 over s minus 1. And again, we're going to split that into 2. So this becomes plus b, which is actually minus 1/13 s over s squared plus 25 plus c, which was 25/13 over s squared plus 25. Okay, now that means that y is going to equal the inverse Laplace transform of capital Y of s. So I'm taking an inverse Laplace transform of both sides of this. And in order to do that, I'm going to skip the step where I just write inverse Laplace transform of this, this, and this. I'm going to evaluate it directly. So notice this is going to be a 1/13 that I can pull out. 1/13 times... where did I write my solution here? Oh, I'm on this one. Yeah. 1/13 e to the t. Okay. Here I can pull a negative 1/13 out, so that's minus 1/13 s over s squared plus 25 from our table will give us cosine of 5t. And then here I can... I don't want to pull the entire 25 over 13 out because this is the one that's going to give me the sine of kt from my table. And remember, I need a k up here where that 25 is equal to k squared. So I want a 5 left over there, which means I should only pull 5/13 out. That will leave me with a 5 up here, and the inverse Laplace transform of that is sine of 5t. Okay, so there is my solution. We have one more example we're going to do of a second order DE, and we'll do that in the last video.